Hi everyone, Natalie Burls here, back to provide this week's Critical Eye from a Science Gal. This time I'll be commenting on Solofelo Mogele's lecture about our essential use of models and understanding the processes maintaining Earth's habitability. Thanks Solofelo for putting together a thought-provoking introduction to modeling. Solofelo introduced us to a number of different types of models, but really it's models of the quantitative kind that we as scientists rely the most heavily on. The type of model we would define as the representation of a system, generally via a set of equations, that allows for the investigation of the properties of that system, and, in some cases, the prediction of future outcomes. So the key elements of this type of model would be a system of equations to describe the behavior of a system. So we would have to develop a system of equations that basically sums up all the physical mechanisms that we think are important in dictating the behavior of the system we're trying to model. And then the second step is to find to develop a framework of solving these equations and some methods to solving these equations. So in some cases it can be a simple set of equations, and I'll give you an example just now, that have simple analytical solutions. Then on the other end of the spectrum, in the more extreme case, there can be a very complicated set of equations, sometimes very nonlinear equations, and for that we have to try and develop numerical methods to find the solutions to these equations. Trying to reproduce physical phenomena with quantitative models provides us with insight into the key mechanisms, so the essential parts controlling the system, and hence the key variables we need to know in order to make predictions. So take for example the previous talk on oceanic circulation. In there we heard a lot about ENSO, the El Niño Southern Oscillation, and how scientists try to make predictions as to whether this will be an El Niño year or a La Niña year. And something that simple models of ENSO have pointed us towards is the fact that we need to know something about the state of the upper Pacific Ocean in order to make accurate forecasts of ENSO. In the Week 1 lecture by Dumusani entitled Not Too Hot, Not Too Cold, we saw an excellent example of how scientists use a simple model with several approximations to gain useful insight and understanding. Remember the bare rock idealization of Mars, Earth and Venus, with no ocean or atmosphere? We asked the question, is the temperature of a planet determined by its distance from the Sun? And then, based on a known set of physical laws, developed a simple model to see if it would yield values close to the observed temperatures on Mars, Earth and Venus. This simple model estimated how much solar energy was absorbed by each planet. This depended on the intensity of the sunlight each planet received, denoted by the letter S, often referred to as the solar constant, which is a function of the distance of a planet from the Sun. The closer a planet is to the Sun, the greater the value of S. S times the surface area of each planet perpendicular to the Sun's rays yields the amount of solar radiation incident on each planet. We then subtracted, so here we have the intensity of solar radiation reaching each planet, which is a function of the solar constant and the surface area perpendicular to it, which is pi times the radius squared of each planet. And then we subtracted the amount that's reflected, so that was the albedo times the incident solar radiation, to get a final estimate of the amount of energy that's actually absorbed by each planet. Similarly, when it came to estimating the amount of radiation radiated by each planet, we used Stefan Boltzmann's law, so that it's sigma times t to the 4 is Stefan Boltzmann's law of how much a idealized black body of a certain temperature will be radiating to space. And when we times that by the surface, because this is in watts per meter squared, we times that by the surface area of Earth as an idealized sphere. So we idealized Earth as a perfect sphere, and we used the surface area of a sphere. To estimate that times Stefan Boltzmann's emitted radiation, the amount of radiation that Earth radiates back out to space. And then we said that each planet should be approximately in equilibrium, where the amount of radiation it received is balanced by the amount of radiation it radiates back to space. So here we have the amount, our first calculation of how much each planet received, and this is how much it will be radiating back to space as a function of its temperature based on Stefan Boltzmann's law. And then that allowed us to back out what the actual temperature was by just rearranging these terms. And the temperature we came up for Earth was minus 18 degrees, which is far, far off, in fact the wrong sign, to what we observe the mean temperature of Earth to be around 15 degrees Celsius. So we saw the similar sort of thing with the other planets. Here's the table we sort of had with Mars, Venus and Earth, where based on, we had the incident solar radiation, so S, based on the distance from the sun, and then the albedo of each planet, and our calculated surface temperatures were much, much colder than, or were not all that well aligned with the temperatures that we are actually observed. So for example, this here is Earth. Observed, we see a temperature of 15 degrees Celsius, and our model gave us minus 18. So this is a good example of a model which turned out to be wrong. As it turns out, the estimated temperatures by the simple bare rock model were much colder than the observations. But this disagreement was useful because it told us that our model was missing a fundamental process. It was missing the greenhouse effect of the atmospheres of the various planets. So not only is this a nice example of a mathematical model, but it's also a nice example of a model that was wrong, but nevertheless useful. Scientists are always pushing to make models more and more realistic, and as a result they become more and more complex. For example, modeling Earth's climate and modeling the temperatures on the surface of the Earth, we've come a long way from a bare rock model with no atmosphere or ocean the right distance from the sun. And this is just this slide just shows you here an example of a schematic of a global atmospheric model that's been discretized into a lot of different individual grid boxes where we solve the equations governing atmospheric motion within each of these boxes. And then we even parameterize a whole bunch of sub-grid scale processes that are acting on temporal and spatial scales smaller than the grid size of these boxes. And then we couple this to the ocean as well as to land models and ice models, and these are the sort of models which we refer to as Earth system models. And we used to tackle questions such as how will the increase in carbon dioxide in our atmosphere as a result of anthropogenic activities lead to a warming of the planet in the future. Towards the end of his lecture, Tsolofelo introduced us to what appears to me to be purely a debate about semantics. We have the well-known saying, all models are wrong, but some are useful, contrasted against the statement that all models are right and most are useless. We can clearly say that all models are wrong, in that they are approximations of reality and not reality itself. And then we can go on to acknowledge that despite not being right, where reality is defined as right, some models are found to be useful, like the example I just gave with the bare rock model. Likewise, if we acknowledge that approximations are implicit in all models, we can say that they are mathematically correct in the way that they are formulated. And because they involve approximations of reality, this may lead to some of them being useless. So really, despite sounding contrary, these two statements both speak to the fact that mathematical models are approximations of reality that have the potential to provide us with useful insights into real physical phenomena. Because models are idealizations of the real world, the word model is sometimes used describe purely an idealized conceptual view of a system. For example, the 3-cell model of the atmospheric circulation talk that you heard. It's an effective idealization of large-scale atmospheric circulation into the large-scale Hadley circulation, Ferrel circulation, and polar circulation. So even though it's not reality, it's an effective idealization. In reality, atmospheric circulation is far more complex. Okay, well, that about sums up what I have to say about why scientists use models and find them useful. Thanks for listening, and enjoy the rest of your habitable planet journey.